Okay, so the DOM, these help us find our x-intercepts. Okay, polynomial functions. Polynomial functions are basically any functions with one variable, not multiple variables. So notice, won't like it pretty much all the time in this class it'll be x. When you get a little higher up in pre-cal, maybe even calculus and physics, I think they start using t a lot for time. But in this class, most of the time it's going to be x. So you should only have one variable in your original equation. That is it. Let's see. Well, let it be the degree of a polynomial function is the highest power. So here the degree would be 5, 4, oh, actually 6. We have to multiply all this together. 6, 5, 2, because that's the highest one, etc., etc. Now, polynomial functions also will have whole number exponents, and your variable will not be in the denominator, like such, thus giving you a negative. So anytime you have a variable, has to be a variable. Notice it doesn't matter if a number is under there, because that's just a decimal. But your variable cannot be under a radical or in the denominator for it to be a polynomial function. Now, this is only important just for an FYI. It's not like I'm going to ask you, is this a polynomial function? But these are going to be what we're dealing with in this entire chapter. Just so you know, you're not going to have anything like this. Only that. Anyway, polynomial functions. One thing you do remember, though, later, if you see something like this that asks you for the degree, essentially, one way you could do it is just how many x's are there? Well, I don't want to be misleading. When you FOIL everything out, there's going to be 6 total. And remember, the degree also tells us, and I think we mentioned this yesterday, the number of possible roots and zeros you can have. That is the most number of possible roots and zeros you can have. That's right. That's square root of 2 times x squared. The x is not under the radical. So this might as well say like 1.3 x squared. Good question. Other questions from this screen? All right. Determine which functions are polynomial functions. Well, I guess they will ask you one. But these are real quick. Yes, it is. Yes, it is. Yes, there's a fraction, but the x is not part of the denominator, so this is good. No, it isn't, because that's in the denominator. No, it isn't, because we have a fractional exponent. And no, it isn't, because, again, variable in the denominator. And that's all there is to those. Yes, yes, no, no, no. Oh, and identify the degree. What would be the degree of this one? 3, highest power. This one? We don't worry about those. There's also, I don't get to that here. I might be jumping the gun a little bit. There's also something called the leading coefficient, which is nothing more than the number being multiplied by your highest power. So your leading coefficient on this one will be 6. On this one it will be 7. That's going to be very important for the next thing we look at. So you have to know your highest degree before you can know your... Yes, you have to know, exactly. You have to have identified your highest power before you can know which leading coefficient is. All right. Graphs of polynomial functions. You'll notice polynomial functions are awesome because they're nice, smooth, constant graphs. There's no breaks in the graphs. There's no holes. They're just, and they're fluid. There shouldn't be any sharp corners in a polynomial function. No sharp corners, no breaks, nothing like that. So all of ours will be something like this, all smooth lines. We can have an infinite number of terms depending on the degree. But so for instance, this one's probably of degree 3. This one's going to be of degree 4, etc. So, all right. Which graphs are polynomial functions, do you think? What do you think about 11? Yay or nay? Yes. All smooth, no breaks. 12. No. Corner. Bad. 13. You're right. Discontinuous. 14. All right, you got it. But don't feel... Would anybody like me to elaborate about why it's yes or no? I know we kind of sped through it, but if you have a question, then please ask. Hey, your new seat is back there next to Aaron, right in front of him. Thank you. Nobody has questions about this? All right. All right. End behavior. Yesterday we talked about it, and I even said, I can't believe they would teach us yesterday's lesson without first teaching us this, because this would have helped you yesterday. The end behavior. You can immediately look at a polynomial function and know, you know how at the end of graphing these, you put arrows pointing one direction or another. You can immediately know where those arrows are going to be pointing just by looking at the function if you use the leading coefficient test, which is actually quite simple. And here it is. The first thing you look for, if your exponent is odd, if your degree is an odd number, cube, fifth, seventh, etc. If it is an odd number, they're going to be going in opposite directions. You're going to have one pointed up, one pointed down. And I'll tell you about which is which in just a second. But which means as x goes to negative infinity, one of them is going to be going down. As x goes to positive infinity, one of them is going to be going up, or vice versa. If your exponent is odd, those are your two possibilities. And just remember x cubed. That'll help you remember that. If it is even, they're going to be going the same direction. Either touchdown or touchback. I don't know. So anyway, they're either going to be going up or both going down. Next thing you look for, once you've just figured out whether it's odd or even, then you look at your leading coefficient. Hence the name of the test. If it is a positive number, then it's going to look just like x cubed. It's going to be negative on the left, positive on the right. You're going uphill. If it is positive and odd, you know what? Let's just make ourselves a little simple chart. Let's make ourselves a simple little chart. We'll call it the end behavior chart, the EBC. So this is going to tell you the exponent, the sign of the leading coefficient, and finally end behavior. Exponent, sign, and behavior. There's only 4 possibilities total in this whole chart. The first 2 are that the exponent is even. The last 2 are that the exponent is odd. And then, if it's even, the leading coefficient could be sign of the leading coefficient. It could be positive or negative, and then likewise positive or negative. Those are the only 4 possibilities. Before we even talk about what their behaviors would be, it could either have an even exponent with a positive coefficient, even exponent with a negative, odd exponent with a positive coefficient, odd exponent with a negative coefficient. Now, I don't care how you do the behavior. You can draw little pictures, whatever. But it's important to know what I'm talking about when I say in behavior. That means as x shoots off toward negative infinity on a graph, you know, this arrow is just going to keep going left. As x goes toward negative infinity and as x goes toward positive infinity, where's our graph pointing? That's what I mean. And left to right, even positive, it's going to fall to the left, rise to the right. Or you could look at these little symbols that they have here. Even negative, it's going to do just the opposite. Rise to the left, fall to the right. Another way I might do this would be negative infinity, positive infinity, because they're all going to be infinities. Positive infinity to negative infinity. Oh, poop. I'm sorry. Shoot. Yeah, I got these 2 back. I thought I was doing the odds. These go down here with the odds. I thought I was doing the odds. Sorry. Negative, positive. Yes. Well, I just haven't done the even yet. Yeah. Oops. Sorry. I just meant to write that with the odd ones. I apologize. So odd. Odd positive means it's going to go from negative infinity to positive infinity. Odd exponent with a negative coefficient, and it's going to go from positive infinity to negative infinity. They'll always be infinity. Now, with even exponents, that's going to be these 2 scenarios. Even positive, it's going to go positive, positive, like a touchdown. Even negative, negative, negative. And if you also want to, I don't know what page this is in your book. Is someone in the book following along? 304. If you want to make a little, just write it on your notes, page 304. That's where this chart is. You can come back and check that on your own as well. Would anybody like for me to leave this up here for a minute? Okay, moving on. Alrighty. So, if you know that test, these three problems are literally that quick. In behavior of the graph, first off, what's my degree? What's my leading coefficient? Notice, my degree is odd, so look at your odds, and my coefficient is positive. Odd positive had what in behavior? Negative positive, or in other words, it went from negative infinity to positive infinity. Now, here's how it's going to look on your test. This is how they always do in behavior on tests. As x goes to negative infinity, y, which they write as f of x, goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. That's the exact same thing as this, but they always write these in there first, as if we couldn't already know that. They're saying, to the left, it falls. To the right, it goes upward. Right here? Yeah. From the chart, the degree, this is what you had missed before you got here. The degree was odd, so I knew it was one of these two, and the leading coefficient was a positive 5. So odd positive gave me falls to the left, rises to the right. And that's on page 304, by the way. So, number 21. Rather than write them out, just say this. Is it even or odd? Even. And is it positive or negative? Positive. So, even positive, what's my end behavior? They both go to positive infinity. I just wrote this because I didn't feel like writing this every time. You know, you could write up, up. You could write 2 up arrows. You could do 2 plus signs. I don't really care. As long as you know that this is how your answers are going to be formatted on your test. No. See, even positive was upward, upward. Oh, not there yet. No, what? No, wait. Odd, positive. Wrong way. Odd, positive was negative, positive. You mean the way I wrote it up here? No. What is in behavior? It means as x goes forward that way a long way and that way a long way, what's y? That's basically what it's saying. So this is standard. This says as x goes way to the left, as x goes way to the right. As x goes way to the left, the y values are getting really small, or going down. As x goes way to the right, the y values are shooting up. That's what that says. This part is standard. This is necessary for any in behavior. This just says to the left and to the right, and this actually tells us what it is. This is the one part that will change every time. It's the signs in front of the infinity. That's what makes this problem potentially hard on your on the test, because all 4 answers look the exact same. The only thing that's different is the combination of positive and negative. Only thing. Does that make sense? Yes. It's specifying so that you know this one implies the left-hand side, this one implies the right. It's only function. That's why I don't even bother writing it. Those are good questions. Very good questions. Other questions? All right. Number 23, even or odd? Even. Negative or positive? Negative, so this is going to be down, down. And I don't even care if you write it like that on your homework. Or negative, negative. I don't care. They all say the same thing. That means it's like that. It's like it's making an N. Lowercase n. Lowercase. Questions about 23. Moving on. Alright. Find the zeros for each polynomial function. Well, this is actually very similar to what we've been doing. So, what's going to make this part 0? What's going to make this part 0? Negative 4, and negative 4 is occurring twice. Why is that important? Because if I asked you to graph this, here's what you would need to do. First off, let's put all the stuff we've learned together right now. Oh, poop, you'd have to multiply it out first. Nonetheless, let's go ahead and plot these first. At positive 5, it's going to cross. And at negative 4, it's going to touch, but we still have to put a point there. Now, if you were to FOIL all this out, well, to save us the time, I'm just going to do that real quick. X squared plus multiply 3 by 2, 2x. Oops, didn't see the last one squared. X. You're going to have to do this every time, unfortunately. You do have to do this so that you can actually... Does this one ask us to graph it? No. That was wrong. I have to restart it. I forgot to FOIL it. Actually, before I bite off more than I can chew, let's answer the question at hand first. So I show you what these questions are asking us. I'm getting ahead of myself, doing things that students didn't even ask for. Find the zeros. 5, negative 4, negative 4. The multiplicity just means how many times do they occur. Well, you can kind of knock out that step if you just list every time they occur. Otherwise, you could say 5 and it happens once, and negative 4 and it happens twice. But if you just write it out like this, you take care of that. State whether the graph crosses the x-axis or touches the x-axis at each of these points. Well, if it happens an odd number of times, any odd number of times, 1, 3, 5, 7, whatever, it crosses. So crosses at 5 and touches at negative 4. Exactly. Any one that happens an even number of times, it just touches. Yep. So let's just do, that's all it asks us for right now, so let's just do that for now. What about this one? Where's it? What are the zeros? 3 times. 3 times. So that one crosses at both 3 and negative 6. It actually crosses at both 3 and negative 6 because they both happen an odd number of times. 29 and 31, you have to factor a little bit. This one's going to be x. You have to factor that a little further. Is that minus? Somebody a good factor in here? Minus 1, I think it's x minus 1 squared. When you factor that. Of course, you could just do quadratic formula. If you're not a good factorer, no problem. Try to find a way to get it down into, if you're not a good factorer, find a way to get it down into a quadratic, and then you could just do the quadratic formula on it. Like if I did the quadratic formula on just this piece, that'd be 2 plus or minus over 2. So 2 plus or minus 0 over 2, which gives me 1 twice. So now I know the other two must be the opposite of this. So x, x minus 1, x minus 1. So you can kind of factor by doing the quadratic equation if you prefer. Because these are the actual zeros. These are what are going to make those equal to 0. Well, let's see, your answer would be, what's going to make this part equal 0? 0. So the answer would be 0, 1, 1. It would touch at 0. Nope, I'm sorry, I said that backwards. Touch at 1, cross at 0. When you factor out an x, what's going to make this piece by itself equal 0? just a 0. There's nothing happening to it. Any x by itself will represent a 0 root. So like Adam, for instance, let's say one looked like this. The roots for this one would be 0 5 times and 1. Okay? Alrighty. Anytime you have to factor something with a cube, in this book, I can pretty much guarantee you it's going to be some kind of factoring by grouping. Just like we did in the first chapter. And that is how you're going to have to factor that, pull out the same thing. But again, all you're looking for are the roots and whether it crosses or touches at each of those roots. No, it was just, we factored out an x and got this whole thing. When you pull an x out of this, this is what you're left with. So the x rendered us the 0, and the equation itself rendered us the 2 1s. Was that your question? What meant? Oh. Well, what would be your first step in factoring this equation? You can, I'm glad you brought that up. You can only do that if x squared is your biggest one also. This has a cube in it, so it throws off the entire quadratic. You can't do quadratic until your degree is 2. Now this piece has a degree of 2 and you can factor it like that. So if you ever see something with x's and everything, take out as many as you can. What I mean by that is, let's look at a quick example. Let's say you had 3x to the 7th minus 4x to the 10th. Okay, what's the most x's you can take out of both of those? 7. So the x to the 7th, which leaves you with 3 minus 4x to the 3rd. Now you have 7 of these, and you could work with that separately. Okay? Alrighty, so moving on ahead. Yeah, we have time. Well, but I can't believe they're not putting all this together first. Are they not? Yikes. Yep, there it is. Okay, what do we get to look forward to? Let me ask you this. Let's just talk about this in theory. Let me go find a picture of a graph. Any graph. Okay, here we go. Look right here. We have a root. Would you agree? Root. What can you conclude about the y values on opposite sides of a root? I hear the word opposite. Who said opposite? What do you mean by opposite? That's right. Well, they won't always be the exact same number. Not all of them are going to be perfectly. But if it crosses, then one of them has to be negative. One of them has to be positive. If it's going to cross, that has to happen. One of these is going to have to be negative. One of those is going to have to be positive, or vice versa. So all that this is stating is, this entire slide is saying, sometimes your zeros are going to be ugly, like 0.3758. You can't find that. You don't have the tools to find that without using a calculator. So all you have to do is do the intermediate value theorem. Plug in these two numbers, and if there's a sign change, if one of them gives you a positive and the other gives you a negative, then you know there has to be a 0 between them. It has to cross from positive to negative. So all you have to do is plug these in, see if one gives you a positive, one gives you a negative, and if they do, you've got a 0 in between them. And it's a yes or no question. Let's look at one. Like 33. Plug in 1. It's 1 minus 1 minus 1. So this one gives you negative 1. Plug in 2. 8 minus 2 minus 1 gives you 5. Is there a sign change? Yes. This one has a root between 1 and 2. And that's all you're looking for is a sign change. Now, if one of them equals 0, then you've stumbled upon a root. And that's a better thing to have than just yes or no. So you're just looking for a sign change. Plug in negative 1 into this one. You get 2 minus 4 plus 1, negative 1. Plug in 0, you get positive 1. Is there a sign change? Yes. So there is a root between those. I know you guys still have to finish up yesterday's assignment, so we are going to put all this together tomorrow. I'm going to adjust this and cut off this bottom portion. That's what I need for you today. I need you to finish up yesterday's assignment and do that today. That's only 10 questions I can do. Actually, we're on 38. Don't be like that. Actually, I'm going to change this since I'm cutting off the hard part of it. There you go. There you go. Now I'm going to quickly